So thank you everyone for joining today. Welcome to our session 5 of our Microgrid webinar series of IEEE Palouse Tech Talks. So we would like to invite our guest, Dr. Anurag K. Srivastava, who is an associate professor at the School of Electrical Engineering and Computer Science. So Dr. Anurag K. Srivastava is an associate professor of electrical power engineering at Washington State University and the director of Smart Grid Demonstration and Research Investigation Lab within the Energy Systems Innovation Center. He also has a joint appointment as a senior scientist with the Pacific Northwest National Laboratory. He received his Ph.D. degree in electrical engineering from Illinois Institute of Technology in 2005. His research interests include data-driven algorithms for power system operation and control, including resilience analysis. Dr. Srivastava is served as an editor of the IEEE Transactions on Smart Grid, IEEE Transactions on Power Systems, and IEEE Transactions on Industrial Applications. He has delivered 30 plus keynotes, tutorials, distinguished lectures in more than 15 countries. He is author of more than 300 technical publications, including a book on power system security and 4 patents. Thank you very much for joining us today. You can take it over from here.
All right, thank you so much. So I appreciate the opportunity to speak with the IEEE Palouse group, and looks like there are people joined, not only in US, but maybe outside. So thanks again, everyone, for joining. And today I'm going to talk about resiliency and how microgrid can be used to enable the resiliency for the distribution systems. So if you look in the recent years, there has been a lot of hurricanes, and there's been a lot of weather events, either it's a wildfire or storm, and we keep hearing this news that which caused the power outage. Other than weather event, of course, there are some threat about cyber attacks, but the essence is, that these events are more in news. So California outage, as you can see here, that because it happened because of winds and wildfire too. Then another one, recently that Con Edison had in August 2020. And then in this region, Eastern Washington, North Idaho, several thousands of people lost the power because of, again, high wind. And all these events, what does it show us? That electrical grid power, that we have electric grid is reliable, but may not be very resilient. And there's a reason for that, because we never design our grid to handle these extreme events. So what do we need, to solve this problem? We need to find out that what is causing these events and impact. So first one is, of course, increase in extreme weather event, right? And that just what I just talked about. And then our grid is aging. And if you look at the DOE data, which came a couple of years before, like let's say transformer. So average age of transformer should be around 42 years, but it's already much more than that. So grid is aging. And the third, there are more reasons, but another important reason is that more distributed energy resources and edge devices are being connected, which means that our operation and control and even market paradigm is changing a lot. So with all these changes happening, we know that these extreme events are basically demanding a superior grid resilience. So next we should look at that what can we do about it, right? So first is we need to define that what is resilience. And if you look in the literature, there are multiple definitions that exist. Most of definition in some way talks about critical load, because we know that during extreme events, we cannot keep up with reliability, and which means that we cannot keep up with all the connected load. One definition that we have in our research group is ability of the system to supply all its critical load, even in the presence of multiple contingencies. And just talking about multiple definition, multiple working group, you can see that there's a IEEE PS Power System Dynamic Performance definition and metric for resilience working group. There's a T&D working group. There is a there's a lot of these acronym here, but basically it's pointing to that IEEE and CIGRE has a multiple working group who's working on defining what is resiliency. The one that I recently came across from FORC is the ability to withstand and reduce the magnitude and or duration of disruptive events, which include the capacity to anticipate, absorb, adapt to, and rapidly recover. And out of these, we like these words, and we have been working on a few years now on ability to anticipate, ability to withstand, which is basically kind of absorb, and ability to recover. So these three things are important, and we try to develop a metric which will measure these ability to find out that can we anticipate well against a certain threat, can we withstand or absorb a certain threat, and can we recover from after the damage has been done. Right. So other than monitoring, defining resiliency, the next step becomes how do you monitor it, which does require you to find the metric. That's what we want to monitor. Just like a reliability, we can monitor stability, we can monitor security of the system. So we want to monitor the resiliency and also look at the different ways to enable it. And enabling need to come from both sides, which means within the field, in the physical system, and the way we monitor the grid right now. So in the field, we have to have a multiple things, new sensors, change the control paradigm. Of course, put more and more microgrid, maybe put mobile generators, which can go and connect to different points and power up, let's say, hospitals. And this has been used by military for some time now. So the distribution grid has to have a predefined microgrid. Otherwise, we cannot create a microgrid on the fly, because microgrid does require some kind of controller and management system. So we have to predefine it. We do have some flexibility in terms of boundary and other things, but there has to be some coordinator to coordinate within the microgrid and keep the voltage and frequency going, and also ability to connect with the distribution grid and ability to isolate and automatically operate its distribution grid. The second part, which is on the monitoring side, which is control center, we have to integrate more and more tools. Either it's a distribution management system or at the microgrid management system. So that requires developing a new tool, which we call it resiliency management system. So just like you have energy management system, we have a advanced distribution management system, we have EMS, energy management system in transmission, we have a microgrid management system for microgrid. We will need a resiliency management system which should fit with the existing operational and control paradigm. So it should be able to use the similar kind of data which is used by ADMS. And if it is in microgrid, then it should be able to use the similar kind of data at the microgrid level. Today, I'm going to focus on these two parts, which is microgrid and the management system, which is talking about resiliency with distribution and with the microgrid. So first one, let's talk about monitoring, and I will quickly go through that, instead of focusing more on this, because I do want to talk about enabling with the microgrid. So in monitoring, I just talked about fork definition and ability to anticipate, withstand, and restore. And these are the three characteristics, or these are the three things that I want to measure. And with the goal is ability to keep supplying critical loads. And these three are at different kind of different time of the event. So one is a before event, one is during event, right? And one is the after event, because you have to recover after event or restore, right? So first question in anticipate before event become that how well my system is prepared, how well the grid is prepared to anticipate the damage on the system. And we are talking about like, let's say wildfire, how well we are prepared, how well you're prepared for the tsunami event or snow avalanche. In withstand, we want to find out how well system can keep supplying the critical load even this event hits in the system. And both of these, mostly you can do something in planning. So it is not something that we can do in a short time period to enhance the anticipate or enhance the withstand. But in restore, this one, we can do in operational, and we already do it in a sense that we do reconfiguration, we do switching, we shift loads, and those kind of things we already do in terms of restoration. But the goal is reliability. If we shift from reliability to resiliency, we will do the same thing, but with the different optimization function and with slight different objective. So these three things, which is basically we call it AWR, anticipate, withstand, and recover. You have to define it that it is a blue sky, which means there is no event, everything is working fine, normal operation, and even the single failure will be part of the blue sky, right? And then the black sky day, where you don't even count that into reliability factor, is where a big event is predicted, next day, or maybe sometimes few days in advance, and sometimes very short time, just few hours in advance. And then from here, we want to recover and then maybe go from gray sky day where some load are outage and then go back to the blue sky day. So these are part of the not operation, but will be a planning exercise. And what we want to do is, again, measure this anticipate metric, which will tell me how much prepared I am, withstand metric, which will tell me that how robust my system is and ability to absorb, and then finally recover. And all of these will follow with certain action, certain plan. So before this black sky happened, and I'm transitioning from year to year, I can do this proactive action. And these will be done to minimize the damage or to minimize expected damage on the grid. And then of course, restoration, which we already do it, we have to do it in a new way, keeping resiliency in mind. So like I said, that I'll keep it brief, and this one basically tells that how do we compute our metric, and it's driven by collecting multiple factors which will impact my ability to provide the critical load under any given event, given the threat. And we assemble those factors and integrate using a multi-criteria decision-making process. And we have used AHP, analytical hierarchical process, which you see here. We have used Shochet integral. So different, any possible multi-criteria decision-making process will combine these factors and give you a single, or crunch those number and give you a single number, and that will be our resiliency metric. This is a different, typically, what performance-based metric means. So if you look in literature, there are two different kind of metric. One is performance-based metric, which is like reliability. And then one is a characteristic-based metric or system-based metric, which will be like stability. So ours is system characteristic-based metric, which depends on network, which depends on the control, which depends on the resources, and depends on the critical load location. It doesn't require using some graph theoretical approach to find the topological factor. And it requires, looking at the different control and even crew and fleet. Now, all these factors, if it's not available, it's not that metric will not work. It just that metric will not represent that specific factor, which should be totally fine, because these are not being used to compare two different utility. These are being used to compare the two different operating scenario of the same utility. Okay, so that they can know that what to do to improve their resiliency. So once you take that, and I did not go into much detail, but the concept is assembling the factor, combining it, and crunching the number to get the AWR metric, and then finally combining that to get the resiliency metric. So for example, this result, I can know that how well I am prepared against, let's say, tsunami, against earthquake, against avalanche or volcano. I can compare robustness of my network or my system and can tell that if the event lasts for a few hours, how my resiliency will go down. I can use it to tell that how well I will recover, how much time it will take. And that does depends on the control that we have, of course. But all these metrics will tell me, and I can compare the resiliency for the system with certain proactive and corrective control compared to another proactive and corrective control. And I can decide which one to go for. I can even compare these metrics to know that where to put my battery, where to put my automatic switch, which is manual right now. So a lot of these things can be done. But the main thing that I want to talk today is about how do I enable resiliency, especially with the multiple microgrid. And if you look at different possibilities of enabling resilience, it goes all over the place. And here are a few listed. So we can do something in planning. We can do something in just before the event is going to happen. We can do something after the event happen. So long-term planning will, of course, use include like grid hardening. So change your overhead lines to underground, which we all know it will cost 10 times more money, and we cannot use it all the time. But if you're in Alaska, it's better to do it, and that's what they're doing, right? So one-time investment, but more resilient system. So depending upon where you are, it will make sense or it will not make sense. We have to put some vegetation management. We know that, of course, the tree work as a fuel or forest work as a fuel for wildfire. So if you're trying to defend against a wildfire, we need to manage the vegetation and also predict that if based on satellite images or based on whatever data we can get, we need to predict that how any event will spread and what will be expected outage. We can apply machine learning, we can apply data analytics, and there are some tools out there which are able to do it. In sensor deployment, again, this has to be done much in advance. We can put micro PMUs in distribution system. We can put more like a fault recorder so that we know that, in future to look at those set of data and analyze that. You can do upgrade of poles. We can do infrastructure upgrade. We can put a lot of backup mobile generators. Just the other day, I was looking at the news that California is putting the call for, for these mobile generators, which is plug and play, and they can use it for, especially in the future, against wildfire, and especially if they do a PSPS, which is power system shutdown in advance. That's what they do to defend against wildfire. They can move these mobile generator and power those critical loads. Then the other thing we can do is implement a distributed optimization or distributed control at the edge, and it will be definitely much more resilient compared to a centralized, because the point of failure is single and centralized, while it is not the case in decentralized or distributed. One other important point is the cyber infrastructure and distributed computing, which will support it. So I'll talk about some of these, very soon. In terms of proactive control, we can again find out that where is the damage going to happen, where is outage estimated, and based on that, with the best guess possible, it's very similar to security concept. We always do if-then analysis and find out if this event happen, what will be the impact? But that is for limited number of contingency. Now we are talking about multiple contingency that is happening in the system and how it will impact my system and what proactive action I can take. We can develop a temporary microgrid that does require, driving your microgrid controllers there and having some sort of ad hoc control. I have seen the news about using drone, where you will use drone as a router, flying router, and use that to communicate between the damaged cyber networks, right? So temporary microgrid will require temporary controller, temporary communication link, and but those things are possible and it does require some more investigation. Then deployment of moving generators, which is very similar to, acquire those mobile generators and then put it, and then backup power support to individual critical facilities. In terms of corrective control, again, it is very similar to restoration, the way we do it now, but with a different focus, knowing more about weather information other than your typical trouble call and smart meter based outage detection. Distribution automation, DR coordination can be utilized in a best possible way with the battery, with or other inverter-based resources. We can have a microgrid with changing boundaries, network microgrid. Of course, this is very important, that how much crew you have and how do we manage them to repair things as the things is going on. So this is, again, not a complete list, but a good list of what can be done to enable resiliency. And I'm going to talk about 2 or 3 different use cases to show it. Before I talk about those, I wanted to clearly point out that what we're enabling resiliency technique we use, it is not going to be a single silver bullet. So one which can work in flood is not going to work in storm or wildfire. One which will work in weather event, of course, will not work in a cyber event. So each threats need to be detected, that where is the utility, where is the grid, and what kind of threat it has. And based on that, we have to decide that what will work and what will not work. So let me talk about some use cases. I'll talk about 3 use cases. So the first one, well, all 3 somehow relate to this proactive control, and some relate to corrective. And in this proactive control, our concept, or basically the key concept has been that if live component goes out of a system because of any weather event, will cause more problem for the grid compared to component if it is planned ahead and taken out in a step. Now in transmission grid, we know that that would be definitely much more advantageous because of cascading outage that can happen. In distribution grid, cascading outage is not expected because there is no mesh network except very few number of cities. So that will not be a problem. But if we'll show the results, if we plan in advance to take out those components which is already going to go out because of a weather event, the overall resiliency will be enhanced. And we can do it using set of information from the measurement devices, like let's say DPMU based, or if there's no DPMU, then using the switching action in well plan, especially if we have all 3 different kind of switches: automatic switches, remote switches, and manual switches. So how do we plan those in well in advance so that the minimal outage happen for the critical load. And the last one will be just using the microgrid as a resource for distribution system, like let's say voltage control, or using it for, of course, the same optimization framework can be extended for other kind of services. So these first two use cases are proactive control. And the use case one is, as you see here, that we are assuming that there is a distribution system, and we can predict that how the storm is going to travel in the system, which part it will impact. And based on that, I can predict that it will take out some part of the system. And before it does that, we will isolate those parts in advance. Okay. Now, what is the difference? The difference is that because I'm planning in advance to isolate those, I will call it shift and shed load. So we call it shift and shed. And we are doing it in such a way that the minimal load goes out of the service, and especially the critical load. And in doing this shift and shed, I can use the PMU data, because if you have PMU data, then I can find out the flow in the line, again in advance, not in advance, but based on the measurement at a given time, that how much load I need to shift so that this line flow becomes 0 and 0 and 0, because that's what we want to take this line out, because this is going to go out anyway because of a weather event. So I need to find a set of control that will make this line flow very close to 0, while with the minimal shedding of load or shifting the load to another feeder, another line. So this coordination can be done, several minutes in advance before the event is going to hit. And in this case, this event is going to take out this transformer because that's where the path is shown. And we show that results that if I do that, the shift and shed using the PMU data, in uncontrolled, of course, the frequency will just go out of bound, while in preventive island formation, I can control the frequency and it will come down and well controlled. So now you can go into all the deep mathematics, that how do we do that, resilience, shift and shed, proactive control. And I'll again not go into detail of these because these are available in the papers, but essence is finding out the change in delta expected and change in delta threshold that we set, and comparing this by doing the each shift and shedding of load till we make the flow on that line equal to very close to 0, and then we take it out before it was taken out by the event. So some more result, you can see that with the multiple network microgrid, which was basically shown like this. So these islands, some are microgrid and some are not. And these microgrid has some resources, and we can see that with different configuration of resiliency resources, we can look at the resiliency. And of course, as we use more and more resources, resiliency will go higher. And without using that, if that specific line or transformer is hit by event, then resiliency will be almost 0. And with DPMU or with distribution PMU, you can see that each feeder resiliency, some are lower and some are 0. While with shift and shed control, using the DPMU, I can get to a good number. Better than before, right? Not, of course, not 100% because we cannot, we don't have a spare transformer in the system to replace it. So this is only about restoration. So we cannot get to the very good resiliency score because some resources are gone in the system. We cannot keep providing all the loads connected. So I'll get into the use case 2, which is kind of extension of use case 1, but without DPMU. It is purely optimization method, but keeping in mind two things, that there are some switches which are manual and requires 45 minutes to 1 hour before sending the crew and opening that switch. And you're talking about event is going to hit, so we have to do it in advance. So here you have a basically distribution network, which has some island, which are predetermined, and some of those are microgrid, some are not. And then we have a bunch of database, coming from there, which is some are real time, some are not real time. And system network is of course not real time. And then we have ADMS in the control room, which has topology and switching information, which has some DR dispatch strategy, some logistic and resource allocation. And then we have the R tool, which is resiliency management system, RMS, that we have developed. And it uses, first estimation of threat, which we need to know, and resiliency metric computation and metric driven optimization for proactive control. The concept is saying that if we know that this is where the event is going to hit, and this is where the component is going to go out, we want to make those components go out in advance so that the impact on the system will be less and less, and it will be well planned by using manual switches. And of course, automatic switch is not a problem. So you can do it like in a few minutes before. And that's why we call it 2 stages. So in stage 1, open manual switches. Stage 2, open the remotely operated switches. Of course, automatic switches is not a question because that will have its own intelligence to open. Goal here is maximize the critical load. So we have this critical load, and then we have a non-critical load, which has a less priority, but we also want to capture it with in certain way as much as possible. So we applied this developed algorithm, and this was mainly driven by this system in Alaska, which is a Cordova system. And you can see that this is how it looked like. There are some hydro here, then some hydro here, and then there are a bunch of diesel generator and some battery. So in this system, we made certain assumption. This is, of course, islanded microgrid system because this Cordova is not connected. I mean, it's a big city, not big city, but a big town. And it's not connected with any other grid system. So it's a islanded, isolated microgrid. And then IEEE 123 bus system, where we assume there are 2 macrogrid and then other systems are not. With the expected event, these are the component which is going out, right? So this black one, and this one will be impacted, and we want to transfer it to some other event or some microgrid so that we can minimize the load outage, especially for the critical load. So we assume some automated switches, some manually operated switches, and then we open and close some switches as needed. In 2 steps, stage 1, manual switches, stage 2, automatic switches. So this is again a proactive reconfiguration, right? And so very similar to 123 bus system. This 45 node, which is simplification, will look like this. And again, this is the event. This is the area impacted by the event, and this is the area impacted by the event. And the gray part is basically requires proactive disconnection, but still we can save the other part. There's a battery shown here, there's a diesel generator shown here, and then the hydro. So here, in terms of different action, we are operating in normal mode, which is, we call it economic mode, not a resilient mode, because it's kind of conflicting if you look at the economic mode and resilient mode, because some of the resources you will dispatch it in a different way if it is economic mode compared to a resilient mode. If we know that there is an event forecasted and it's going to impact, then we need to find out resiliency metric, and based on that we need to find out how much resource requirement are for battery or from other resources. And then we solve stage 1 optimization problem, which means that find out proactive switching in the network of using manual and switches. And then once we figure it out, then we go to the stage 2. So of course we send the crew to do it. And in stage 2, we take the remotely operated switches and we operate it just like a few seconds or a minute before the event is going to hit. So you have to formulate that, and there will be objective we already know, the maximize the critical load and non-critical load with certain weighting factor. And then you can think about multiple different constraint. So these are radiality constraint, radiality enforcement in microgrid, isolation of the faulted part, because of course we don't want any faulted part to be part of the system. And then we want to keep the healthy subsystem, including microgrid, within the system to maximize the power there. Then consider the local generator capability limit within the microgrid, without the microgrid, nodal flow balance, line flow balance, and then power flow equation and voltage limits. And then in the stage 2, we want to see at the limit operation and set point generation for healthy part, because the first part already has been done. And then also switching operation we don't want to keep doing, plus of course all the constraint that has been considered here. So this will give us results, and you can see that proactive action that we just did, it will reduce the resiliency a little bit in advance because you're making the system outage, but you can keep this as low as possible while keeping the crew safe, right? Because they are going into the field when the event is expected. And then resiliency overall, as you can see here, is going to be improved compared to if you do not do anything, right? So scenario 1, as you can see, which is this one, that if you do not do anything, then this is how your resiliency look like. And this is for Cordova system, this is for IEEE one receiver system. Scenario 2 is we are doing a proactive reconfiguration, but outage part are removed a priori. And if you have enough remote switches, then you will just remove it a few minutes before. Of course, both happens before the event. So you can see that these two after the event will look like same because all the action is happening before the event, but there will be a difference between these two. Okay. So overall, what is our concern is the resiliency after the event, and this is much better. So let me talk about last use case 3, which is using a microgrid as an auxiliary resource to distribution system. So you have a distribution system, which is modeled by this IEEE system, and then one part of the distribution system is a microgrid. And in this case, we are assuming a small DC microgrid, which has its own management system. And this management system MEMS is connected with or at least exchanging information with ADMS. ADMS will give a set of signal here, which will tell the set point and tell that, okay, I need your sources, maybe reactive power or real power, whatever it is. And that will be provided back to the distribution system and coordinated with the ADMS. So we need this coordination between ADMS and MEMS. And we call it 2 different modes. One is non-grid supporting mode, where MEMS is doing its own thing, managing things, and does not care about providing service to ADMS or to the distribution grid operator. And then there's a grid supporting mode, where grid is coordinating and telling MEMS that if you have more resources available, then give us real power or reactive power. So this one is about reactive power. And it becomes a simple optimization function, volt-var control problem. Of course, it requires some coordination and set point, but done in two time scale. First within the microgrid and finding out that what resources are available, and then ADMS solves this optimization and tells the set point that what reactive power is needed, and that will be implemented within the microgrid. You need to think about all the constraint, electronic interface, and then fast changes is possible, while some other controllers, like let's say tap changer, you cannot do the fast control. So these two timelines need to be thought through in this whole optimization. And with different regulators like capacitor, or in absence of those, we can formulate this whole problem. And then we can show that if you do not do any control, then the voltage, which is this red one, is not very good. And it's for different phases. So you see all the red one is phase A. So with no control, this is the voltage. With control, the voltage will be good. Same thing for phase B, which is a green. So with no control, and with control is here. And the blue one with no control, phase C, and this one is with control. So this is expected. Now the same formulation, I can easily extend it for real reactive power to real power. And you can see that active power injection is of course changing, and not much, but reactive power is changing more. But if I change my formulation, which is right now is reactive power, of course, the real power can be also used appropriately and by coordinating these two ADMS and MEMS. Now the next part, which is the last part, is about what we did is centralized. And there is a one controller which is coordinating all of these. We can make it much more robust and resilient by decomposing it and making it distributed control problem or distributed optimization problem. So in this specific case, distributed, you have to have all the node which is sending the information to the control center, either it's MEMS or it's ADMS, now will talk to each other and that will become distributed. Does not need to, not each agent to talk about with each other, only the controllers need to talk about, which has some action to do. And then I can reformulate this and make it like that each controller is distributed doing its own thing, but finally reaching to the same goal, which is decomposed into the each controller. So I'm not going to detail of this because limited thing can be covered in 1 hour. But important part is that this is needed in future for two reasons. Not only that it is scalable given increase in DER, but also it is more resilient. And it is resilient in two different ways. First, distributed allow us to go for distributed computing. And this project we finished a couple of years before with ARPA-E, where we put this distributed controller, which is modeled in this small devices, as you can see here. So these are digital devices, are representing a digital devices in the lab, and the distributed controller is running REAPS, which is developed by Vanderbilt University as part of this ARPA-E. The good thing is that these node, which is REAPS node, knows how to exchange information to solve this distributed optimization. So I can take the same system, which is kind of work in progress, and then I can put DPMU or PMUs and with the different controllers, and these will talk to each other and solve the problem and will be much more resilient. Why? Because if this one is failed for some reason, it is damaged, other two will keep talking and solve the problem because there is no leader here, right? And then even if this is gone, if this controller is gone, then only one controller can solve the problem because again, there's no lead. So it is much more resilient to not only in terms of physical component and systems, but also resilient in terms of different number of controllers and cyber infrastructure. So, I can talk about this whole thing, distributed computing, and how it will be more robust and fault tolerant, for making the resiliency, enabling the resiliency in the integrate. But we need to think about not only the physical architecture, but cyber architecture and the control architecture. So this is a quick video to, let me see if it runs, to show that, how it looks like in the current state, our resiliency management system. There is a multiple part, as you can see that system information will be collected, very similar to EMS. which will have all the infrastructure, generators, network, load information. We will have the other part, which is resiliency monitoring, which will basically show you the metric that we are computing on the certain map. And the whole goal is that operator is able to see that how is the resiliency in different threat that can happen to the system. So threat preparedness and impact. And this work is always work in progress, because we get some feedback from different people who are trying to use it or within our group, and we keep revising it. So resiliency monitoring will have like changing in time, and would also show you the different factor which is causing this resiliency to go down and go up. And because of that, I can exactly figure out that what to do to improve my resiliency. And that will be reflected in decision support. And then finally, I can do planning and analysis to analyze that if I put a battery, at what location resiliency will go up. If I put a switch, how the resiliency will go up. If I need to put a new cable as a redundant link between two part of the system to make it as a microgrid or even reconfiguration, where to put that. So all these questions can be answered using this tool. So finally, just to summarize, resiliency, we think, is the ability or characteristic of the system, not the performance only. It depends on network, depends on control, depends on resources, and depends on, of course, critical load. Right? It can be improved. It requires a lot of effort in terms of coordinated planning, proactive and corrective control. And we need to keep in mind a specific threat and different operating scenario before deciding that what action is the most appropriate. We need to look at all the different possible control, either it's a proactive or it's a corrective control, and use that in well-planned manner with certain computational tractability. And of course, with the microgrid, which we cannot create a microgrid on a fly, so it has to be pre-planned and with certain flexibility, and that flexibility need to be used to enable the resiliency when these extreme event happens. And we need to keep in mind about value of these dollar amount that we put, enabling it in normal operation, which is a blue sky day, and also in the black sky day, which is a critical operation. With that, I would really like to thank IEEE Palo section to provide me this opportunity, all my research group, who are the one really do all the work, and a couple of funding, which is mainly DOE funding, Radiance, which allowed us to work in Alaska, and Aggregate, which allowed us to work in Seattle, and EY Assist, which helped in Spokane, and WSU campus is going to be a microgrid. With that, thanks again, and I'll be very happy to take more questions. I see that there are multiple questions in Q&A, and there are some in chat. So yeah, I can take those one by one.
Thank you very much, Dr. Srivastava. It was a very informative session.
Hi, thank you so much for talking on the Palo section, and it was very nice to hear your presentation. And I'm sorry for joining late. I just mute myself for Q&A.
Yeah, so we have many interesting questions, so we could try to answer as many as we can.
So I'll go through the chat first or Q&A. I'm looking at the chat first, and
I think,
there.
Yeah, we can go over the Q&A first.
Okay.
So one of the question is, should resilience cover only HALP events, and should it be only considered critical loads or all loads?
So one thing is sure, it should consider only high impact, low probability, because if we are looking at the normal event, then reliability concept is already there. And we have made a lot of progress on like a event which is not a high impact. Okay. Should it be considered only critical load or not? I think because of related life and like a fire department or hospitals, and those are critical loads, airport, your IT department and everything which is connected through internet. I mean, we do want those to be restored first. And those critical load need to be identified by the city and basically, what were the operator that we are dealing with or town we are dealing with. So if every time I talk to different grid operators, their priority is different. So I personally think that critical load is important, but looking at different IEEE and CIGRE, they do not kind of agree on this. So we need some more discussion, on that part, but definitely it should be high impact, low probability.
Okay, thank you. So we have how to interpret if one microgrid has 70% resiliency. What should we understand if someone says a microgrid has 70% resiliency?
Yeah, that's a great question, and something that I being asked often. And just by looking at one number, I cannot tell much. So I need to tell that this is 70% resiliency. If I increase my battery capacity, it's going to be 75. But if I increase my, like let's say switch example that I was talking about before, if I change my manually operated switch to remotely operated switch, that will increase my resilience to 80%. So where to invest? Maybe switch, not a battery.
Okay.
So those kind of question can be answered. It's a relative resiliency.
Okay. Yeah. In system-based resiliency metric, while the event is happening, will there be any short-term predictions or forecast about which loads or which distributed energy resources will be damaged? And if those can be restored immediately or not while calculating the resiliency of the network?
Mm-hmm. Yeah, so great question. I think this prediction, which is kind of evolving field, and not many tools out there which can use data-driven and machine learning and historical and maybe system information to predict. We have been trying our hand on the wildfire prediction and how it will impact, working in California. But this is still a science that need to evolve. But if you can do that prediction in a good way and tell that which load and DR will be damaged, that will be a good, I would say that a big impact on the enabling resiliency. Now, if those can be restored immediately or not, while calculating the resiliency of the network, I think if the event is happening, that is happening too fast. So that time calculating resiliency is not very important, but finding out that next action I can do and my tool, which is optimal based or some rule based or whatever it is, coming up with some options that, these are going to be damaged or are being damaged or already has damaged. And here are the options. My tool should tell you that here are the 5 options operator can implement, and that will increase the resiliency. Right. So,
Pawan, you're muted.
Oh, okay, sorry. Yeah, what are the possible resilience enhancement strategies against cyber attacks, especially operation resilience based?
sure, yeah. So that's something that I did not talk about today, but off the head, I can recall that, of course, just like against the weather, against the cyber also, you can do control action from both the side. So the first point is in cyber, against the cyber attack, detecting it. So detection is very tricky because it will not be reflected into your power grid. And the reason is we have to detect it before it impacts the power grid. Otherwise, after that, the system is kind of compromised anyway. So detecting the cyber attack is the first important point, and which is still a tricky part. After detection, kind of localizing it, that where it is, classifying it, that why it happened, and what kind of cyber attack it is. And then finally, in terms of action you can take is isolating that what were the switches, using the SDN, software defined network if you have, or using some kind of change in routing table. So all the different action you can take to isolate the infected part or compromised part, just like you will do in the power grid. So if the fault happens, it will automatically take out that part. But in reconfiguration, we try to connect it back so that we can maximize the power. Same thing need to be done in the cyber network. And of course, I can go on and on, because that's a great topic, and a lot of work need to be done on that.
Okay. So we will take few more questions. We have very interesting questions as well. So since AHP is constructed with weight ratios of criteria pairs, how do you know that one criteria are more or less important than the other while assigning the weight? What if there is no expert to know the importance of any criteria?
Yeah, so in our, which is all in paper, we did not talk about with the Shapley value and how I can adjust and do the sensitivity analysis of different factors to know about, what factor I should choose while doing the AHP. Now, if I do not, implement my weight in a very best possible way, again, it's not going to impact my result much, because remember that what we're trying to do is compare two resiliency score. But there's definitely an impact of weights and sensitivity analysis and some kind of rule that we can ask the expert to set those is a way to go. Now, if there's no expert to tell me that, importance of different criteria, then I'll go with the default. Just like any other software that comes with a default value and then comes with providing more information, so we can do sensitivity analysis and can tell you that what you need. So both details again are in, we have in papers, but just a quick sensitivity analysis and Shapley value is two ways to do that. Fuzzy
Okay.
Shapley.
Okay. How to consider probabilistic behavior of event path? What if the path changed suddenly?
Yeah. So so that's something that we thought about a lot, and especially working with real utility. Now, you want to delay your decision, as much as possible near the event. So, and that's what we are trying to do here, because if you take some action much in advance, then the probability of your prediction has more error is high and high. But if I look at any weather event, Hurricane Katrina or Sandy storm, we know that 1 hour before, the probability of my prediction going wrong is very less. So you can make it probabilistic, and this is again something that we are working on in extending this AWR, how it will look like in a quantile forecasting. But a lot of time I ask myself that, is that a right way to go? Because even if I can make it theoretically possible, my operator is not going to like it, because operator likes decision and I work with a lot of cognitive science. They want some decision to be taken right away without any probabilistic concept there. So I can do that in behind the scene, but when I tell the operator that, okay, this is the decision they should take, and I can minimize the probability error by minimizing my time to take a control before the event hits. That will be probably a better way to go. Other than that, what we are doing is making my AWR probabilistic and also the action.
Okay. So we'll take maybe a couple more. Should we not usually consider economic aspects when evaluating the resilient enhancement method? If the method is not costly constrained, it might lead to infeasible costs, right?
Yeah. So in planning, we should consider that, and we should try to compare two different possible way that I can put in hardening the system, which I'm talking about several months in advance, several days in advance. There we should consider the cost. But in operation, because those things are already there, and then operational cost is not important. Just like in security, we do not put cost as a top priority. That is a normal scenario. So in resiliency, the cost should take a last priority compared to supplying the critical load. And we have seen in our result and in a multiple paper that has reported that there is a conflict between economics and resiliency.
Okay. So what metrics would you suggest using when comparing resilience against power system inertia? Congratulations for the great webinar.
Thank you. So comparing resilience against power system inertia is not very clear to me. I mean, now, if it is reflecting to the hiccup that power grid operator has to adopt a new technology, of course, if that's that's the question, then it is a challenge, and we have to just wait till NERC put just like NERC SIP for the cybersecurity, which is not about resiliency, but that's at least the first step to keep our grid more and more cyber secure. I'm sure that over the years, as these events are increasing, NERC will come up with some more um, suggestions for the grid to do that. And I see that happening, like, there's some software by different companies related to resiliency is being adopted. Weather.com came up with prediction of damage because of weather events, collaborating with IBM. So there are these so many different companies and solutions are coming. That means that we are going, they are seeing the market, and that inertia of not adopting a new technology, will go away if it comes from the NERC and FERC.
Okay. Yeah, I think we have many other interesting questions, but with respect to the time, we are a little running late. So yeah, we would like to thank you now. We will try to answer these offline if possible, but yeah, we have
I'll be really happy to. So my email is here. Please, if you can send me all the questions and some way, or they can contact me so that I have their email so that I can reply them directly.
We can share your email through the chat, or and then they can send the emails to you directly.
Sure.
Yeah.
I'll just do that.
Thanks. And we are planning to have a webinar on cybersecurity aspects for microgrids, but we haven't finalized everything. So we'll be publishing that soon.
Yeah. So we will be posting our recordings on our YouTube channel for IEEE Palu section. So please do check out that, and also do check out our LinkedIn page and Facebook page. So we'll be posting all the information about upcoming events and interesting facts. Yeah.
Thank you so much. So I just put my email in the chat box, and hopefully, please feel free to contact me, and I'll be happy to answer.
Yeah, so we have participants from all over the world. So thank you very much again. It was very wonderful, and thanks for providing your valuable time with us.
Yeah.
Thank you.
Thanks for the great presentation.
Thank you.
Thank you. Have a good evening, everyone. Bye.
Have a good evening, everyone. Thank you.
Bye.